Thank you very much for inviting me to give this talk. I'm grateful to the organizers. Okay, the subject of group sister algebras is not new, it's very old actually. K-theory is used starting from maybe beginning of the 70s, and from the 80s it was the development started pretty fast, and in the past 40 years there was significant progress. Group sister algebras are used in many areas like representation theory, topology, differential geometry, some questions related with manifolds or non-simply connected manifolds. So I would like to just give a review, a certain, for those who are not familiar with this, an introduction to the theory. It will not be very technical, but still we'll use some tools from different areas like differential operators, differential operators. And let's start with simple things. So what is a group sister algebra? You take a group. If it is a discrete group, you just consider finite linear combinations of elements, and the coefficients, so the G are elements of the group, and coefficients A will be complex numbers. We need really complex numbers because we want to go into sister algebras. And for just algebraic part, the multiplication is like this, and there is an action of the element of the group on L2 of G, on the Hilbert space. And the formula is just exactly the same. So it's just convolution product. Okay, let's do a more general thing, and let's do the same for locally compact groups. So we don't need actually finite linear combinations. We need functions which will act like convolutions. So this is an element of compactly separated function which acts on the which will be used for to create the same kind of algebra using convolution product like this. And this algebra will act on L2 of G quite naturally, because elements act as by shifts, and you just average over your function. The formula is exactly the same as this formula for the product. So the sister algebra, which is the closure of this convolution algebra acting on L2, will be called reduced sister algebra. Actually, there is a bigger algebra which is called full sister algebra, but we'll need only this one algebra, and this will be denoted like this, sister reduced of G. Okay, so if we go into representation theory a little bit, then essentially L2 of G decomposes into some reducible representations. Roughly speaking, direct integral, but in more complicated cases, it's some more complicated stuff. But we can talk about reducible representations weakly contained in L2 of G. And if we look at this algebra, it is responsible for representation theory for the part of representation theory which is contained in L2 of G. the representations, the reducible representations for most interesting groups, say semisimple groups, can be visualized, I mean, kind of by their topology. There is a certain natural topology on this space of reducible representations. And in this topology, for example, there are some discrete points which correspond to discrete series representations which are called square root integral representations. I will give some examples, so I don't want to go into very precise definitions, but you will see in examples how it works for some reasonable groups. To analyze this star reduced of G, we will have to use some usual stuff of C-star algebras. So here I give you some examples. This reduced C-star dual in the case of an abelian group. This is the Pontryagin dual of the group itself. I mean, you have a group. You make like Fourier transform using Pontryagin duality, and what you get is another group which is called G hat, which is the dual. And in simple examples, for example, for R, you make Fourier transform, you get again the group R. If you take a circle and make a Fourier transform, you get Z, the group. So how it works? You on the circle you have just the usual the functions, the exponentials of E. So on the circle you have the functions like this, and then they go into N in Z. This is the dual of the C-star on C-star of S1, and this is this goes into C0 of Z. So this Fourier transform, which is Pontryagin duality in this case, and the backwards, of course, if you take Z, you have Pontryagin dual will be the circle. More sophisticated example is this one, SL2R. This is a non-compact group, locally compact non-commutative group, and there are three different kinds of representations. The principal series decomposes into two parts called even principal series and odd principal series. And also there are some discrete points, discrete series representations. Well, essentially discrete series occur as, if you take representation if you take the action of the SL2R on the Poincare disk, say you take all holomorphic functions and all anti-holomorphic functions and some more sophisticated holomorphic sections of certain vector bundles, you get what is discrete series representations of the SL2R. Principal series are more closely related to the kind of this example to a certain extent. But I don't want to specify exactly representations. Essentially, it means that the group C-star algebra, The group sister algebra of SL2R decomposes into three parts. There are three ideals which correspond to you have a direct sum of 1, 2, and infinitely many sister algebras. K is the compact operators on the space of reducible representation. So you have discrete series, infinite number of discrete series and compact operators correspond to certain ideals in the group sister algebra. And you have principal series which looks like this. It means simply functions on 0 infinity with values in compact operators vanishing at infinity. And A1 is very similar, but it has a certain, there is a catch. At the point 0, the space is no longer irreducible. It decomposes into parts, and the sister algebra of the group contains these diagonal operators. So H prime and H2 prime will be both irreducible. And the fact is that, well, the topology is non-Hausdorff in this case. When the point tends to 0, the representation converges to, let me just go back. At this point, the limit is 2 points at the same time. Okay, so this is a kind of an example which you can expect. In general, it's more complicated stuff, of course. Now, the Heisenberg group case is also pretty interesting. You have the representations which correspond, well, the whole set of representations parameterized by certain parameter lambda, which is the parameter on this real line. Each point of lambda except 0 is infinite dimensional, and so you get this ideal in the sister algebra, which corresponds to the points on this r minus 0 correspond to these points on this real line, except 0. At 0 point, the topology is non-Hausdorff. The point which tends to 0 converges to all representations on the two-dimensional Euclidean space. Two-dimensional Euclidean space correspond to, well, it's just all representations when C goes to 0. All representations parameterized by the duals of A and B. So this will be kind of what you can expect for nilpotent groups, for example. This is a nilpotent group. SL2R is a semi-simple group. Now, let's go to K-theory and try to analyze this thing by using K-theory. K-theory is a certain tool which is originally invented by Atiyah invented by Grothendieck for purpose of algebraic geometry, but in topology and Banach algebras, it was developed by Atiyah, Bott, and other people who were working in this topological K-theory area, mainly in the 60s. So, because we are interested mostly in K-theory of sister algebras, I can define a K-theory for Banach algebras, essentially. We don't need any more in this talk. So sister algebra is closed subalgebra of the algebra of bounded operators on some Hilbert space, usually separable, of course, space. And the characteristic property is that there is the adjoint operator. Now, the definition is pretty simple. You consider all matrix algebras over your sister algebra or Banach algebra, and essentially you don't look at this n, because these algebras are embedded in one another. If it is in Mn, it is in any larger with bigger number n. The two idempotents are identified if they are homotopic in some Mn of B. You can take also direct sum, so it will be a semigroup, a abelian semigroup, and after you use the usual construction of the usual trick, taking differences, you get a group, abelian group. So it's a group defined for any Banach algebra. Now, there are certain properties. Covariance is a very easy property. In B, if B doesn't have a unit, you add this unit and you define K0 as the kernel of this map, mapping the unit into unit of C. And also K1 is defined using just tensor product with C0 of R. So you consider all functions on R with values in B, which with the limit 0 at and both plus and minus infinity. So this gives kind of general definition of K theorem. Now let's see what happens if you take well, it's an important tool. You can that the K theory of an ideal, an algebra, and the quotient are related by this called six-term exact sequence. This is an exact sequence. It's cyclic six-term sequence. And there are some boundary maps which I don't define, but I must say that they are essentially usually in most cases can be calculated using naturality. This sequence is natural if you take other algebra, say B and the ideal J, and you have a map from A to B with the ideal mapping into the ideal, then the sequences map into one another and the diagrams commute. So that's the very important point of the whole thing. Now there is also you can deduce from this Bott periodicity, this very important isomorphism. But also, well, Bott periodicity can essentially is vice versa. You first prove Bott periodicity and then you use the exact sequence. Now, there are a number of things you can look at and consider them as exercises, which follow either from exact sequence or direct definition of K theorem. And the corollary for SL2R is that the K theory decomposes into the direct sum of infinite copies of Z. Now these numbers n correspond for n not equal to 0 to discrete series. Each point in the dual gives you a copy of Z, because for complex numbers you have Z. K0 is Z. And for n equal to 0, let me just let's look at this at this algebra and A1, you use this definition of this A1 as the algebra which has this splitting at the end point. And you use the exact sequence for K-theory, and then you will see that you will see this generator which corresponds to n equal to 0. So it comes from odd discrete series, odd principal series. Also, you can get K1 equal to 0 from the same kind of calculation. For the Heisenberg group, it's slightly more complicated, but essentially it's not a big deal. From the exact sequence, you can get this result as well. You need only to make some work to understand how the boundary map is. The boundary map, which will eventually give you the boundary map has to be calculated precisely. Okay, so now what we actually want is to develop some kind of stuff which allows some more sophisticated calculations. And in particular, it will allow to calculate the general conjecture called the Baum-Connes conjecture, which is proved in many cases and allows to kind of reduce the calculation of K-theory of group sister algebras to some topological stuff. First of all, well, I'm grateful to the previous talk, Professor Hickson's introduction of the symbols and everything, and I will use this. We need essentially differential operators, differential and even more sophisticated operators. So the most simple is linear differential operator, which is like this, and this expression means in local coordinates you take just first derivatives, and these are matrix functions because vector bundles are not necessarily one-dimensional, they may be n-dimensional. And so these AKs are matrices, and you take a certain matrix depending on the point. AK are functions of the point of a manifold, and these are derivatives on coordinates of your manifold. So these are very kind of easily describable operators, but let's look what we can do in general. So as Nigel Hickson said, we would need to consider symbols, and symbols are defined on cotangent bundles. The symbol is a certain map of between the vector bundle. You lift it to the cotangent bundle. So it will depend on not only on the point. It's a function which map which depends not only on the point of manifold but also on covector of the cotangent bundle. And for the simple case of first-order differential operators, you get just you replace your derivatives by multiplication by coordinates, and you don't forget to multiply everything by square root of -1, and the functions remain the same. So you just replace your derivatives by multiplication operators by the coordinate functions. And the symbol is elliptic in this case if it is invertible for any xi non-zero. In more sophisticated cases, you are not obliged to consider first-order operators, but operators of differential operators of higher order, and the idea is the same. To construct a symbol, you just replace nth derivative by this multiplication by the coordinate function. Well, in the case of one-dimensional thing, you just nth derivative replaced by multiplication by xi power n. Even more sophisticated, which we actually need, will be pseudo-differential operators. You see, the replacement of derivative by multiplication is a kind of Fourier transform thing. And in general, to define operator corresponding to a symbol, you have to do Fourier transform, actually. So the idea is to use pseudo-differential operators. Why pseudo-differential? Because differential operators are not bounded. And pseudo-differential operators of order 0 are bounded. So using such operators is a useful tool. You can compose them, you can do some, take a joint, whatever. You get like an element of sister algebra. So using pseudo-differential operators is a very useful tool. And I will show you later how in examples you have a differential operator, you can reduce it to pseudo-differential operators by some normalization. You just divide it by something, and it will be an element of the algebra. So the symbol of well, the operators order 0 are bounded, and the symbol is a certain function as usual. It's just the map, linear map on the cotangent bundle or on the manifold of full tangent manifold of the manifold X. Now, well, to define elliptic operators in this, well, I forgot to say that there is a certain theory, of course, belonging to many people, but probably the last kind of definitive way of defining operators was due to Lars Hermander. So the symbols should satisfy certain properties to be kind of eligible to be considered as symbols of differential operators. Apart from this, if you want to define elliptic operators, we need certain properties of the symbols. We don't require the symbols to be invertible for any x psi when psi is non-zero. We need only this property at infinity. At infinity, we need the symbol to be, well, essentially unitary. We can consider even symbols just invertible at infinity, but this is more useful for K-theory purposes. And we can always normalize symbols to behave like this. So this will be elliptic symbols, and certainly we need Hermitian metric on the tangent space and on all vector bundles and Riemannian metrics on the manifold to define this. But this is not a big problem in general. So if we don't assume X to be compact, then we require this condition to hold uniformly on compact subsets of X. Finally, a small cosmetic thing which is also quite useful is to consider self-adjoint operators. Just put them into matrices like this. Instead of one operator, you consider both operator and its adjoint, and you put A and A star in such a way that this operator has degree 1 in the sense, if you consider this as a graded vector bundle, you consider this degree 1 part and this degree 0 part, excuse me, and this is degree 1 part, and the operator A and the star interchange, so they have degree 1. So the Hilbert space is also Z2 gradient, and differential operators will be degree 1. Now, the main property which we'll use is that the operators of order 0, pseudo-differential operators of order 0, commute with multiplication by functions modular compact operators. So the commutators are compact. That's the main property we will need. Now, what are the topological kind of consequences of all this stuff with elliptic operators? First of all, elliptic operator is Fredholm, which means exactly that it's invertible modular compact operators. Because its symbol is invertible at infinity. The elliptic operators, the operators which have symbols which vanish at infinity are compact by theorem, by the Hermander's theory. So the elliptic operators which have this property that their symbols are unitary at infinity, they satisfy this property that A0 star minus 1 and A star A0 minus 1 are compact operators. And this means in particular that this A0 is this part, you see, we consider our operator as this A0 star. So this both A0 and A0 star are Fredholm. Fredholm operators have finite dimensional kernel and finite dimensional co-kernel. So the kernels of A0 and A0 star are finite dimensional, and so we can define the index of a Fredholm operator as the difference of dimensions of the kernels of A0 and A0 star. In fact, if we go a little bit more into abstract definitions, we could define this group called K-homology of X as the group of abstract Fredholm operators in some Hilbert space where we have a representation of C0 of X, and the properties that this and this are compact, and A0 commutes with the action of the multiplication by functions modular compact operators. So the even the definition of K0 of X can be given using this kind of abstract Fredholm operators with the for certain representations of C0 of X. But we need it only for index theory, and in our case, well, this K-homology K-homology of X is essentially it's an algebraic group, which is a group from topology. It's a topological thing which is dual to topological K theory. Can be defined just purely topologically, and it appears that this group is very useful in in index theory, and it can be defined analytically, as I said, using this kind of operators with combined with representations of C0 of x. Now, to go further, we need some topology, and we need the notion of proper actions. So if you have a locally compact space with the action of a locally compact group, then this is a proper space, or the action is proper if you have this condition that each compact set is transformed to infinity by the group action. You don't have compact sets which have non-zero, non-empty intersection for just a sequence of elements of group which go to infinity in the group. All these intersections become empty outside of compact subset in the group. Another definition is the universal example of the for proper actions. So if you consider well, it can be say definition lemma is that there exists a locally compact space with a proper action of G, such that for any locally compact proper G space X, there is a continuous G map into EG. So it's a kind of universally it just swallows, I don't know, any G action, any proper G action. This map is unique up to G homotopy. The examples are very simple. If you take a compact group, you can take EG just a point. You don't have any interesting spaces for G compact. Any space is compact space. If a space is proper with the action of G compact, group compact, it's just compact space. If you take, say, group Z, then the universal example will be R. So with the usual shift. Now, for a locally compact group, actually, with not only for a Lie group, but for any what is called almost connected Lie group, almost connected locally compact group, there is a maximal compact subgroup in it, and the universal example will be G mod K. This is proved by Abbas. Now, we can now consider elliptic operators on non-compact manifolds, Riemannian manifolds, and we will assume that the action is proper and co-compact, which means that the quotient is compact. The operator will be called operators which we will consider pseudo-differential operators order 0 will be called properly supported if for any function, compactly supported function, there is another function A2 such that the composition multiplication of A1 then your operator A2 is the same as A1. So it means that this A1 doesn't go beyond a certain compact set. If you have a compactly supported function, then the operator doesn't, the image of the operator for any function excuse me, for any function in this, say you have a compact set, a compactly supported function, a section of your vector bundle, then the image of this compactly supported function will be in another compactly supported function, and even the support of this function is bounded by some it depends on the support of the initial function you take. Okay, now we need certain tool which is called Hilbert Model. If B is a sister algebra, then let's consider this example. We take the sequences of elements of B, length n, and we take this product, which is called an inner product. And we do it like this. You take the sum from 1 to n of the corresponding coordinates, and you take the adjoint and the second coordinates. This will be an element of B. And this is very similar to the usual Euclidean scalar product, like in the finite dimensional Euclidean space. This can be generalized in the sense that you can define, there are axioms for such objects which are called Hilbert modulus. This is the simplest example of a Hilbert model, just finite dimensional thing. You can define also infinite dimensional Hilbert space, then you need to take infinite sums like this. But you can also generalize just the usual axioms of Hilbert spaces and obtain the definition of a Hilbert model. The outcome of this is that, I need to say that the norm on the Hilbert model should be related with the product, with this inner product, by this formula. That's important. The norm of the square of the norm on the Hilbert model is defined, should be defined by this inner product, and the Hilbert models are supposed to be complete in this norm. Now you can define operators between two Hilbert modulus. These are operators which have adjoint with respect to the inner product in this sense, and the operator should be bounded. Well, essentially, one can prove boundedness under some conditions. So the important class of operators, as usual, are compact operators, but not compact in the usual sense of some Banach space compactness. It's not this. This is a direct generalization of finite rank operators, and finite rank operators are operators of this kind. You take a sequence of vectors vi, wi, and you apply to your vector u, which you start with, and you get this operator which will be called a finite rank operator. So it means that each operator, for each index I, it is a rank 1 operator, a special definition for Hilbert models. And again, you can call the operator Fredholm if it is invertible modulo compact operators. Compact operators are just closures of such finite rank operators. Okay, so I don't go into any details of this. I want only to say that you can define the index of a Fredholm operator on a Hilbert model so if the kernel and co-kernel kernel T and kernel T star are both projective models over B, then it's just a difference. Difference of the two projective models gives you an element of K0 of B. But if they are not, then you need to make a certain perturbation of your operator to make the kernel and co-kernel projective. Actually, it's enough to make one of them projective, and then another one will become projective as well. So this requires a little bit of technical tools, but it's not kind of complicated, sophisticated stuff. So K-theory can be defined using K-theory of C-star algebra can be defined using this kind of Fredholm operators over Hilbert models. Any K-theory element can be presented like this as a of course, we need some equivalence relation on these Fredholm operators, but essentially it's not a big deal. Now, what is important for us is how to associate an index to a G-invariant elliptic operator. Excuse me. So we have an operator with G-invariant, properly supported elliptic of order 0. Order 0 means pseudo-differential operator of order 0 on a graded bundle E over X. We want to associate an element of K-theory of C star reduced of G. We want the index to be an element of C star K-theory, of this K-theory. And for this, we do the following. We first consider compactly supported sections of the vector bundle. Compactly supported L2 sections. And the operator is properly supported, so this will the operator will map it again into compactly supported functions. So on this, we can restrict our operator to this kind of compactly supported functions, L2 functions, and then we define the Hilbert model structure for these compactly supported functions with values in C star reduced with values in C star reduced of G. First of all, we define on this the inner product like this. We take this triangle of brackets denote that we take it's not an inner product in the Hilbert space. It will be a new inner product. It's the new inner product which will be an element of C. Where is it? In this algebra. So we take the convolution algebra. It acts on this space of functions. On this space of functions, we have an inner product with values in the convolution algebra. It's defined like this. It's defined like this. It's just the dependence on G is this one. And this is the scalar product in L2 of E. So so the fact that the action is proper means that this is a function with that this compactly supported functions that this is compactly supported function of G. If G goes to infinity, this vanishes. outside of compact subset. So we define the inner product with values in this algebra, convolution algebra, and then we prove that this inner product is good enough, satisfies the axioms, positivity, etc., and we define the new norm on this space, and complete in this norm and get a Hilbert model over B, which B is just the sister algebra. So we make this space first a model over CC of G with inner product with values in CC of G. Then we define the new Hilbert space, Hilbert model norm using this new inner product and get a Hilbert model. The operator becomes an operator on this Hilbert model. It's important that the operator is G-invariant, otherwise it will not work. The operator is G-invariant, and if it is elliptic, it will become elliptic and Fredholm on this Hilbert model. So this is a very important part of the whole story, because you can make out of any elliptic operator which is G-invariant and has good properties on the manifold which is not compact. You make an operator on the Hilbert model, and so the operator becomes elliptic and gives an element of sister algebra. Gives an element, an index in the yes. So now it's just a remark that we can make even better. We can make give a general definition and abstract elliptic operators, which this uses not necessarily manifolds, but you take just a representation of the group and the representation of the C0 of X in some Hilbert space, and you essentially define the index theory of such thing with values in a sister algebra, with values in the well, this is an abstract version of operators on a manifold, and this still gives you an element. This still gives you an element of the K theory of sister G. So the abstract elliptic operators are elements of this group, and you get an element of kind of associate to an element of this geometric group, an element of K theory of group sister algebra. Now, what is called the Baum-Connes map or assembly map is this map from abstract elliptic operators, G-invariant elliptic operators, to K theory of group sister algebra. You can take the limit of these abstract groups overall X with G compact X and get this group. By definition, it's this limit, and so you get this assembly map from a certain geometric group into K theory of sister algebra. It's important that left-hand side consists of certain kind of abstract elliptic operators. Okay, let me probably skip something here. What I want to point out that for the case of the case of G mod K, where G is a Lie group and K maximal compact subgroup, we will need the following fact, that this abstract group with the action of G reduces actually to this abstract group with the action of the maximal compact subgroup. This is an important thing. Now, there are some examples, and I briefly mention, first of all, of course, in the case of R, you can calculate everything explicitly. It's not really a very interesting thing. Compact group, say circle, everything calculates completely explicitly, and you get, what is important is that this assembly map appears to be an isomorphism. In each concrete example, you get an isomorphism for the, but these are all very simple examples. More sophisticated example is this one, SL2R, and you can check directly. We already know that the K-theory is calculated like this, but there is also a calculation for G mod K. As I said, this reduces to the case of the compact group action. And G mod K in this case is a Poincaré disk. K is the group, just circle rotations group. And so there is a Bott periodicity which tells you that this is just R of K, which is the same as this one. This doesn't prove you need to follow exactly the definition of the assembly map to get really that there is an isomorphism. But these two guys at least look similarly. And the case of Heisenberg group also pretty similar. It has both parts are the same. Now the Baum-Connes conjecture is that these two the assembly map is an isomorphism. Now let me briefly mention. I probably will be out of time very soon, but let me briefly mention some applications. First of all, if you what is a Novikov conjecture? If you have a compact manifold without boundary oriented manifold, and you denote by L star the Pontryagin-Herzebrug class, then the conjecture, F will be the map into the classifying space. The classifying space is the space classifying all free actions of the group G. All free actions. So the universal cover will map into the EG, which is the universal cover, which is the contractible space covering BG. So the conjecture says that F of this element in this group is homotopy invariant. In other words, if you define the highest signatures like this, the highest signatures corresponding to each element Z of the cohomology group, you pull it back according to by this map, and you consider this product, and all these high signatures will be homotopy invariant. The important contribution was made by Mishchenkov, who defined a universal constructed homotopy invariant symmetric signature in the certain wall group. This wall group maps into this group, and it appears that if you consider this element here, when you map it into this group by the assembly map, you will get exactly this element which comes from the Mishchenkov signature. So in this group you have already a homotopy invariant thing, which is Mishchenkov symmetric signature, and the fact that your left-hand side maps into this group exactly in this element means that the conjecture actually states that when you map a certain element by the assembly map, it becomes homotopy invariant in the right-hand side, in this group. In this group, it will be in the K-theory of sister algebra, it will be homotopy invariant. So if the assembly map is injective for this group G, then the left-hand side element defined by higher signatures will also be homotopy invariant. So the Novikov conjecture follows from the injectivity of assembly map. That's the main thing. Now, let me list some results without any details and who contributed. It's just a big number of people who contributed. The important thing is that the Baum-Connes conjecture is proved for all almost connected locally compact groups, amenable locally compact groups, closed subgroups of rank 1 Lie groups, hyperbolic discrete groups, discrete co-compact subgroups of certain SL3 groups, countable subgroups of GL2K for any field K. But even for this group SL3Z, the Baum-Connes conjecture is not known until now. The Novikov conjecture, which is now one refers to the Novikov conjecture as usually a strong Novikov conjecture as the injectivity of the assembly map. This is proved for much larger. For example, it is proved for any closed subgroup of almost connected Lie groups. For example, for any groups like SL3Z, whatever groups which are embedded into Lie groups or embedded into countable subgroups for countable subgroups of linear Lie groups over any field. It is known. It is proved, but not in general. Not in general. In general, even the injectivity is not known. Now, let me briefly, just in one word, say something about two other applications. First of all, Dirac induction is a certain, say for let's look at semisimple Lie groups. You have a maximal compact subgroup. You have this group, which is the geometric part, the geometric left-hand side of the Baum-Connes conjecture, and you have this the group which is the right-hand side, the sister algebra of of the group G. If we assume that G mod K is even dimensional, and this is and the action of the K group on this space is spin, then what happens is that so this is completely calculable. This is isomorphic to R of K. So for each element, so the left-hand side of the Baum-Connes conjecture is just R of K, the representation ring of the maximal compact subgroup. So this group is generated, the K0 of G mod K is generated by the one bot element times any representation of K. Now the bot element is just this kind of thing. It's a multiplication by the coordinate function times times Clifford multiplication by the dual element of the Clifford algebra, Clifford multiplication. When you make a Fourier transform, when you pass from the symbol to the operator, the corresponding operator on G mod K will be what is called Dirac operator. The Dirac operator is exactly has this symbol. This symbol. If you take the tensor product with any fine-dimensional representation of the group K, which means twisting with this representation lambda, you will get just tensor product with the Dirac operator on a vector bundle tensored with this vector bundle, additional vector bundle. And what happens is that you can reduce the Dirac operator to order 0 by using this kind of operator. You just normalize it in this way. It becomes 0 order. And you consider the index in this group. This gives you for each element of R of K, you get an element of this group which is exactly the an operator. This is exactly the Baum-Connes isomorphism, which is called Dirac Induction. For some groups, for some representations lambda, it gives a discrete series. In this case, the representation of discrete series is realized on the kernel of such Dirac operator. That's what happens in the what corresponds to some representation theory, which was already known in representation theory, but it's kind of naturally comes from K-theoretic point of view. And finally, the Kadison-Kaplansky conjecture states that if G is a countable torsion-free discrete group, the conjecture is that any idempotent element in this algebra is either 0 or 1. This conjecture follows from Baum-Connes conjecture. So if the Baum-Connes conjecture is true for G, then this Kadison-Kaplansky conjecture is true. To prove this, one needs certain observations. So first of all, any element of this group is an index of an elliptic operator on some G-compact G-proper manifold. And since G is torsion-free, the action on X is free. Second thing is that there is a trace. There is a trace on this algebra given by this formula. So you define the trace. It's finite trace and faithful. So we can compute the trace on the index of an operator. We can realize any element of C star reduced of G as an index of an elliptic operator, and then we compute trace on this. Now the point is that there is an Atiyah's index theorem which says that any element, any G invariant element, the index, this trace of the index is exactly the index of the operator, which you can descend your elliptic operator to the quotient because it's G invariant and the action is free. You can descend it to G x mod G, and this index is an integer. So this trace on the index is an integer. And then, well, you just prove that if because the trace is faithful, the only situation when it is an integer can be that the trace is 0 or 1, because you consider the trace on a projection. You consider trace on a projection, and this trace, if it is an integer, it can be only 0 or 1. Thank you.